All right, so now that we've had a look at the exam and the solution, let's see these announcements here. A week from today, you've got your next homework assignment due. By the way, the most recent homework assignment has been graded by the grader, and you can pick that up after class. It's on the table back there. We're going to start talking about flow types and flow visualization, which is in Chapter 4. And so far in the course, all we've done is talk about fluid properties and hydrostatics. And hydrostatics means that the fluids aren't moving, that they are static. But fluid motion is really important. And part of the reason why fluid motion matters so much is that most of the time the structures that you'll be designing as an engineer are dealing with fluids that move. For instance, we're trying to get water through a dam to generate electricity, or piping water from a drinking water production facility to a house, and then conveying wastewater from a house to a sewage treatment plant, and so on. So fluid motion matters simply because that's what engineers do, is take action to move fluids around. And so we have to have available to us equations that will describe the motion of fluid and answer questions like how much energy is needed to move fluids from one place to another, and what will be pressures at a certain point in a pipe network, and so on. Broadly speaking, there are two main approaches for dealing with fluid motion and tracking particles. And one of these approaches, the Lagrangian approach, is trying to answer the question, what is the fluid velocity by tracking individual particles as they move through space? Now, this is a really computationally intensive process for a couple of reasons. One of them is that particles in motion don't follow a straight line path. They can move in 3 dimensions. And we're going to be talking today about different types of fluid movement, both laminar flow and turbulent flow. Most of the time flow is turbulent, which means that particles have, in a way, kind of random flow paths. And so one of the challenges of keeping track of these particles is just the very unpredictable paths that they take. And another thing is that there are so many particles. If you think about the number of water molecules that are in a liter of water, it's in the billions and beyond. And so the problem with the Lagrangian approach is keeping track of all the particles. Each particle can be described in terms of its motion in 3 dimensions, x, y, and z, or I, j, and k, depending on how we're going to describe the notation. And the velocities are changing over time. And so it's not just that they each have a different velocity, but over time, each particle has a velocity that's changing. And so the Lagrangian approach is challenging, and because of that, another way that we can look at fluid motion and try and answer the question, what's the velocity of fluid, is instead of tracking particles, what we'll do is we'll look at windows in space. What I mean by windows in space is just consider a fixed field that fluid is moving through. You can think of it as a mesh or a net. And if you divide the flow area into segments, then you can assign all of the particles within a certain flow area the same velocity, a representative velocity. And obviously, the smaller and finer the mesh, the more accurate it's going to be. So that if you break up the Ohio River into a channel that's only 4 fields wide, then that wouldn't give you very much resolution. It's kind of like a picture or a TV screen. You know, a 4K TV screen gives you a sharper image because each of the pixels is smaller. But back in the bad old days when televisions had a resolution of about 500 vertical lines, the pictures look kind of blurry and not very sharp. And so the Eulerian approach is a similar thing. It will track the velocity of particles as it flows through a field, and then all of the particles inside of that field are assigned the same velocity for a certain time. Now, it's still challenging because the velocity can potentially change if we have unsteady flow, but what we do is we just say we're going to ignore that. We're going to ignore that inside of this fluid element, their particles may have different velocities. We're just going to say on average they're going a certain direction. And by just sort of ignoring the noise, we can solve a lot of problems and and find answers to things like what's the energy loss as water travels through a river and so on. All right, so that's a little bit of background. Let's take a look at this picture and do some image analysis here. What do you think you're looking at in this picture? What's happening? It's an expensive car, or a model of an expensive car at least. It looks like even the model is fancy, right? And maybe it's solid gold, although more likely it's probably modeling clay or something. But what else do we see besides the car?
Wind.
Wind. How do you know that's wind? What suggests? I mean, we can't see, you know the old saying, you can't see the wind, so how do you know it's there? You know? It doesn't exist if you can't see it. But we see something. What are we seeing? Looks like smoke, and I heard the word airflow. Okay, so let me ask you this. If there's wind, what direction is the wind going? Is the wind coming from the left towards the right, from the back towards the front? Can you guess at the direction of the wind? Isaac? It's from the right towards the left. And how do you know that? Okay, all right. It appears to be dispersing on the left. The smoke, it's like a tracer. This smoke is a tracer that when we put the smoke in, it's giving us an idea of what's happening to the surrounding air. So in a way, this is kind of, each one of these lines is representing the wind around it. We can think of it as flow fields in a sense. All right, so it's more dispersed on this edge. There's diffusion, as it's called. You know, like if I threw a smoke bomb in the corner of this room or a tear gas canister, that would be a great way to end the lecture one of these days. But so let's say a tear gas canister goes in the corner. It would begin spreading out slowly, even if we didn't have a fan, even if we turned off all of the ventilation in the room, it sealed up the doors and windows, held perfectly still. The gases would still slowly move through the room, and that transport phenomenon is called diffusion. And so here we see both advection, which is the bulk flow of a fluid, like the wind going towards the car, that's advection. But additionally, there's diffusion, which is where the smoke is getting further and further apart. So that tells us about the direction. So we can see, just from the image, that the wind started here, and it's going there. All right, so congratulations to us. We figured something out. What else can we see from the picture? What do you think it means that the lines are getting closer together? Any guesses about that? All right. So it's obviously, we know the physical object that's causing that. But what does it say about the wind? Any guesses about what it means about the wind itself when those lines get closer together? It's being displaced. What do you mean by displaced? Okay, good. What's this thing on the back? What do they call that? Spoiler or a wing? Have you ever seen like one of those on the back of a Hyundai? I have. I mean, probably they're not needed on the back of a Hyundai, but why is it needed on that one? Okay. This car, in a way, is similar to a wing, right? The way that a wing works is there's wind, and so the wind that goes under the wing is going slower than the wind that goes over the wing. The wind that goes on the top of the wing has to speed up to match the wind that, you know, like if you start here, you have to end at the same time. And so it has to go faster over the top so that it can catch up with what went underneath. And that's a very simplified description of what we'll get to later in the semester. But the point I'm making here is the smoke shows us that actually the air is moving faster. The velocity is changing as it flows over that car. So these lines getting closer together is a representation of a change in fluid velocity. The fluid here is air rather than water. Sometimes we keep thinking of liquids and you know, a lot of fluid mechanics is about gases as well. All right, so any questions from this image so far? We're going to talk about different flow types today. Sure.
In a realistic setting, like say you go outside, there's no wind, still accelerate the car on the highway, is it considered wind or is it something different?
Good question. So the air is stationary, but the car is moving. Then I guess we probably wouldn't call it wind, right? Because wind is the movement of air in the atmosphere. But I think the relative motion of the gas over the air over the car is the same as if it was the wind blowing. That's an interesting point, though. All right. So what we were looking at in the previous picture was a physical representation of something called a streamline. A streamline is useful because it can indicate the direction that fluid is moving, but from the streamline we can't exactly see the magnitude of velocity. You know, those little smoke lines didn't tell us if the wind was going 20 miles per hour or 200 miles per hour. We don't know. Maybe we could try and estimate it from the diffusion, you know, how quickly the smoke was spreading out inside of the wind tunnel. But what these streamlines show, they're the light blue lines. The little arrows show us the direction of flow. And this picture on the left is open channel, meaning that it's a river or a canal, some sort of a channel that's open to the air. And some of the clues that this is open to the air is, number one, this thick black line underneath. This is meant to be like a solid surface underneath. So here's the riverbed, and there's nothing on top of that. And then also all these little dashed marks here are sort of meant to visually suggest the ripples of water. In some other texts, and sometimes when I'm doing drawings, it's common to put a little triangle at the top. And that also indicates a free surface of water. And so what that would mean is, you know, here's water, and the triangle that's on top of it means that it's touching air, rather than this image on the right is an enclosed flow inside of a pipe. And so we're looking at a cross-sectional view, but it would be a circular pipe that's enclosing this flow. And the way we know that is that it doesn't have the ripples. You know, it's got the solid surface on the bottom and the top. But still, the streamlines are indicating the flow direction, and that they're parallel tells us a little bit about the velocity. That these streamlines are parallel tells us that the velocity isn't changing. And so that's an important interpretation. That is not true on these upper images. This picture is a tank that has a hole in it. We call that an orifice, where water is discharging out into the air. And so you can see from these blue lines the direction of flow, and also the fact that since these blue lines are changing direction and getting closer together, then that tells us that the velocity is changing as well. So a change in velocity is acceleration, and we'll spend a good part of a future lecture talking about different types of fluid acceleration. You can see here is a representation of a wing, and the streamlines go over the wing and underneath the wing, and we've just talked about, you know, that the velocity on the top of the wing is higher than the fluid velocity underneath the wing. But it's interesting to note that here is a streamline that just stops. There was some wind that was moving towards the wing, and then it stops because it intercepts the leading edge of the wing. And it causes a localized increase in pressure along the leading edge of the wing. Okay, water is flowing in this image through a contracting channel. And so it's a pipe that's getting narrower. And we can tell that the velocity is speeding up. The velocity of the fluid is speeding up because those streamlines are getting closer together. Just like it did in this picture of the car, the velocity of the air was speeding up when the smoke lines get closer together. So over the top of the passenger cockpit, the wind was getting faster. The same thing is true here. Now, you can have velocity as a vector, and so it's got both direction and magnitude. At the center of this pipe, it's not the direction of flow that's changing, it's the magnitude of the flow. Its speed is increasing. In the rotational flow that's shown on the right, it's not necessarily the speed that's changing, but the direction. And so we'd still say that there is a change in velocity, and therefore that there is an acceleration. If you have flow going around in circles, and there's a big example of that flow going around in circles right now in the southern Atlantic Ocean, like a hurricane about to hit Jamaica and Haiti. And so even if the winds are going in the same speed, the fact that they're changing direction means that there's acceleration. So streamlines are very useful for helping us to see what's going on inside of a flow situation. We can break up flow into uniform flow, which means that the velocity is constant in the direction of flow. So here, since these lines are parallel, that means that the velocity isn't increasing. So dv ds, the change in velocity with respect to position, is 0. There's no change in velocity. Non-uniform flow is when the streamlines are curved or they're not parallel, so that means that as you move from left to right, for instance, as you move from the wider end of the pipe that's contracting to the narrower end, the velocity has changed in the direction of flow. That's non-uniform. It's the same picture, yep. But what we're doing is we're breaking it up into categories. And there's going to be a table that gradually over the next several lectures you'll fill in different ways to characterize flow. And one of the big differences is uniform versus non-uniform. And why we're talking about this is which equation you use to tell you what is the pressure or what is the velocity is different depending on whether the flow is uniform or non-uniform. So you kind of have to, like a doctor diagnoses an illness before deciding which medication to use, the engineer has to kind of diagnose the flow conditions before you know what equation to use to solve problems. And so you'll have to look at pictures and read problem text and try and understand based on what they're saying about the flow situation if you've got uniform flow or non-uniform flow. And based on which of those it is, then that'll lead you down a certain computational path. Another way to classify flow is steady versus unsteady. So uniform versus non-uniform is about position. Is velocity changing with respect to position? Whereas steady versus unsteady isn't about position, it's about time. So it's how are flow conditions changing from one moment to the next. And steady flow, what we're saying in steady flow is that they're not changing. So a river that has the same depth and the same flow rate from one moment to the next is steady flow. Unsteady flow is when either the velocity or the depth, some characteristic of flow, is changing over time. Now, a streamline, like we've been seeing how streamlines can help us diagnose whether conditions are uniform versus non-uniform, but we can't tell from streamline pictures whether the flow is steady versus unsteady. So look at these pictures. The pictures do tell us uniform versus non-uniform, but they don't tell us steady versus unsteady. Why not? Okay, because steady versus unsteady is with respect to time, and a picture just tells you what's happening in an instant. A series of pictures will tell you what's happened over time. And in fact, let's look at a series of pictures that show us what's happening to some flow over time. This is someone was out on a hike and saw something pretty interesting while they're on the hike. This is in Arizona.
Oh, there it is. Here it comes.
Hiking up a stream bed. Oh, I sure wish that projector was a little brighter, but you can see
Wild.
Conditions are
Whoa,
unsteady.
It's coming quick.
It was a dry riverbed when they started the hike.
Awesome.
Flash flood. That's right. It was
Should I probably
raining
get out of the way?
upstream in the watershed.
Oh, yeah, I get up. You're good.
Oh, they'll find higher ground eventually. Otherwise, we wouldn't have this video.
Dang,
right?
it's bigger than the last.
Unless it's like a Blair Witch situation. So, flash floods are awesome. It's one of the things I study in West Virginia, based on how steep the watersheds are.
It's bigger than the
It would
last.
take longer. Now look at that. Isn't that a roaring torrent? That is a lot of water. For sure.
We know what to look
When they get to
for.
start the hike again.
That's crazy. It hasn't even been raining.
Arizona. Havasupai. Yeah, here in West Virginia, we still have flash floods, but they're a lot slower than it is there because we have a lot of trees and vegetation that, before the rain gets to any certain point in the channel, it has to wet the tree canopy, and then it has to wet the ground surface, and then the forest litter has to get wet, and then it can finally start to move.
So it takes longer. How long does it take?
That's a good question. Last year, I was on sabbatical leave in the UAE, and the conditions in the UAE are similar to what we just saw in the video. And so what I'm trying to do is compare a West Virginia lag time, is what it's called, from when it starts to rain to when you see the peak flow. West Virginia lag time to the UAE lag time, because the slopes are about the same for West Virginia holler and a UAE wadi. The slopes are about the same, but the difference is vegetation, and that's what slows down the flow here. I've looked at a watershed out near Target. Everybody knows where Target is, and it varies depending on the size of the watershed and also the intensity of the rainfall, but I measure about 40 minutes is the time from when it rains to when you see the peak flow. And by comparison, in the UAE, same size watersheds, similar rainfall event, the time was closer to about like 12 minutes. So, the tree canopy and all of the leaves that are on the ground really slows down the flow quite a bit. Okay, so I hope that when you think about steady versus unsteady, you'll think to that video, and it'll help you to remember the difference between the two. Steady would be when you look at the Ohio River. It doesn't change much from second to second. I mean, from one day to the next, the levels will go up and down, especially if it's been rainy, but it does not change rapidly. Okay, so far we have uniform versus non-uniform, steady versus unsteady. Here's a completely separate way to classify flow, and that is laminar versus turbulent. Laminar flow is characteristic of slow-moving water, has a low velocity, it appears very tranquil. It would be streams that are moving at a very low speed with a relatively shallow slope in the stream, or fluids that have a high viscosity. And so we can calculate the Reynolds number by multiplying the density of the fluid by the velocity of the fluid and the diameter of the channel that it's flowing through. So a pipe diameter, for instance. And then divide that by the absolute viscosity of the fluid. And if the resulting unitless number is below 2,000, then we know that conditions are laminar. Turbulent, on the other hand, is a Reynolds number greater than 4,000. And in turbulent flow, there's a lot of random movement of fluid particles. So, if it's water flowing through a pipe, if conditions are laminar, then a single, fluid particle that's going through the pipe is more or less going to stay in the same spot relative to the pipe wall as it moves downstream. This would be laminar conditions. If you have turbulent flow, though, a single particle is going to have a very random path as it generally moves downstream. It'll still have a lot of random behavior. That's because there are collisions of particles colliding with each other, colliding with the channel edge. And in laminar flow, the collisions are sort of cushioned by the viscosity, whereas in turbulent there is so much energy in the collisions that it sort of disturbs its original direction and results in a lot of random movement. So here's a cross-section on the bottom that represents what happens in turbulent flow. As you can see, this dashed line represents the velocity profile, the average velocity profile, but from one moment to the next, at any single spot, it may be a little less than the average velocity, it may be a little more than the average velocity. And this has a relatively flat nose also. And this flat nose just means that if you get away from the center line, the average velocity is still about the same as what it was in the center line. But that's not the case at all. In laminar conditions, this maximum velocity location at the center line of the pipe is actually double the average velocity. And so the average velocity would be the point at which half of the velocity is to the right of the line, half of the velocity is to the left, and the peak velocity at the center line of the pipe for laminar flow is double the average velocity. We'll get to see, like with our own eyes, laminar versus turbulent flow in a future lab experiment. For those of you who are taking lab with me, remember that blue dye that I said would stain your hands? We'll be using that to actually see laminar and turbulent flow in the lab in a week or two. But I'd like you to get some experience with the calculating of the Reynolds number. Like I said before, it's unitless. That sometimes throws people off when they're expecting units, but they all cancel out. We've got two questions here. Number one, or step A, if you have a velocity of 0.1 meters per second and a diameter of 2.5 meters, then what's the Reynolds number? Now, you know how we say the standard unit weight for water is 9810? The standard density for water is 1,000 kilograms, 1,000 kilograms per cubic meter. All right. The standard viscosity for water, unless something else is specified like a temperature, is 1 times 10 to the minus 3 newton seconds per meter squared. So that's the viscosity you can use when calculating the Reynolds number. All right, so if we want to know what is the Reynolds number, water moving at a very low velocity, 0.1 meters per second, is very slow. I mean, if you were challenged to walk that slow for a few minutes, it would be agonizing how slow moving that is. But still, even though the water is moving very slowly, that's still considered turbulent flow. A Reynolds number of 250,000 for a velocity of 0.1 meter per second. So here in part B of this question, it's asking what's the maximum flow velocity that the water can go through the pipe and still maintain laminar conditions. And so what we're saying there is let's let the Reynolds number be equal to 2,000 and solve for velocity. And so for that one, if you're solving for the velocity that will still maintain laminar conditions, then it works out to 0.8 millimeters per second. Now that's dependent on the diameter of the pipe. So you can change the velocity required for laminar conditions by changing the diameter as well. If you made the diameter smaller, then that's going to decrease the velocity required for laminar conditions. And the pipe that we have back in the lab is, I think, 1 centimeter diameter pipe. And so water doesn't have to go 0.8 millimeters per second for us to still observe laminar conditions. But you'll actually be able to see just how I was drawing this pipe. You'll be able to see with your eyes a stream of dye that mainly stays together when conditions are laminar. And when conditions are turbulent, what happens is that it's going all over the place, and it's also starting to diffuse and just become diluted inside of the flow. So you can visually see the difference between laminar and turbulent flow. I got a good question as you were working on those calculations, and that is, what's in between 2,000 and 4,000? Because obviously it's 2,000 and below, 4,000 and above, so that middle ground is called transitional flow. And whether the flow is going to be spreading out, meaning like sort of turbulent conditions or laminar conditions, depends on what direction you approach transitional flow from. So let's say, for instance, that you had the water moving very slowly through the pipe and conditions are laminar. And so you're gradually increasing the velocity through the pipe, and maybe you're opening a valve to gradually increase the velocity. And you're doing it very, very slowly, and now you get to the point where Reynolds number is 2,000. Well, if you open the valve a little more, conditions are still going to stay laminar all the way through the transitional range, and they'll become turbulent at approximately 4,000. But if you were in that range of like 3,000, and then you hit the pipe with a hammer, introduced some turbulence or like irregular movement, then that could shock the system to begin seeing turbulent conditions. And so the opposite is true, that if you had a high velocity and a big Reynolds number, and so that the flow, you've got the dye spreading out all over the place, if you're gradually decreasing the velocity and therefore decreasing the Reynolds number, it's going to stay turbulent through the transition range until it gets closer to 2,000. Now, it's not exactly 2,000 and 4,000, but it's kind of remarkable. In the lab, we'll try and identify that threshold. Like, I'll be showing you, all right, I'll be turning the valve very slowly, and we'll try and see when does it seem like the dye is starting to become diffuse and irregular movement in the flow. And it's remarkable how close to 2,000 and 4,000 we'll get when we're just doing that visually with some instructional equipment back in the lab. All right, so other questions on this? Yes? This is absolute viscosity. Kinematic viscosity, and I'm glad you mentioned that actually, because there's an even simpler way to calculate Reynolds number. So an equivalent formula for Reynolds number is just velocity times diameter divided by kinematic viscosity. Right. So you can calculate Reynolds number this way, and the reason why is if you look at this formula, that formula, it's got both viscosity and density in it. And so remember that kinematic viscosity is absolute viscosity divided by density. So I told you that the typical value for absolute viscosity of water is 1 times 10 to the minus third Newton seconds per meter squared. And we know that the typical density of water is 1,000 kilograms per meter cubed. So the typical value for kinematic viscosity of water is 1 times 10 to the minus sixth meters squared per second. And you can use that to calculate the Reynolds number, and then it saves you one substitution. So here's the table that there's a lot of empty space underneath right now. We're going to begin filling in this comparison of uniform versus non-uniform, steady versus unsteady. Because like I told you before, it's when you're diagnosing what kind of flow that you've got that tells you which equations to use to answer things like what's the pressure at a certain location and what's the velocity of flow at a certain location. So if we're comparing what these two different types of categories define, the key difference between uniform and non-uniform is how velocity is changing with respect to position, whereas steady versus unsteady is all about time. All right, so streamlines we've talked about. We've seen those blue lines that are streamlines. There's also something called a path line. And a path line is just what it sounds like. If you trace a path line, that shows you where a particle was over time. It's just sort of the path that it took. A streamline is showing you at one instant what is the direction of flow, whereas a path line kind of shows the historical movement of a particle. And the third kind of flow visualization line that we'll look at is what's called a streak line, and it's also about what's happened over history, but rather than tracking a particle, it tracks the movement of flow at a certain position. So let me show you what I mean about that. These definitions, I hope, will become a little bit more clear. Consider the following scenario. We've got water before a certain time that's moving to the right. T naught is just like a dividing line in time. It's just, like BC and AD. Okay, so T naught is just before that time, the water was moving to the right, and then it was moving upward and to the right. So there's two different time periods and two different flow directions. Now let's look at this picture. Here's before on the left, on the right is after. So remember what we said is that before the flow was going to the right, and then after flow was going up and to the right. Okay, so these blue lines are the streamlines. They're showing the flow direction. So to the right before and upward to the right after. Okay, this is the path line. That dashed line is sort of like, what if every second we draw a dot where the flow is? And then you can see after the flow direction changed, then the path of the particle also changed. It just follows the same direction indicated by the streamlines. So does everybody understand path lines? It's just showing the path of the particle. Streak lines are a little bit more tricky. And before I show you the picture of streak lines, the answer is no. It's not just the mirror image of the path line, because that's the first question I get. Every time I show streak lines is the students just ask, well, do I just like draw a mirror image of the path line? And it's just coincidental that they look the same in this first illustration. With a streak line, what you're doing is you're staying at a certain location. I'm going to stay here, and I'm going to inject, let's say, a tracer, like a dye. In other words, what if I took a can of paint and I started pouring it into the water, and I'm pouring it into the same point, but the flow is moving downstream. So think about what if I was standing on the bridge pouring paint into the Ohio River. Then you could see that paint flowing downstream, and that's what this is. See this right end of the line? That's the first paint that got poured in. This is the beginning of time, T naught, because I was still pouring it at this location, but it got pushed to the right because of the direction of flow. The flow direction is indicated by these streamlines. But then at T naught, the flow direction shifted, and I'm still pouring paint into the same location, but when the flow direction shifted, now you can see that this is the paint that I poured in after the shift in flow direction, and right here is that first part of the line. This is that first bit of paint that I ever poured in. So here is T naught, and then here is the present on a streak line. So it's called a streak line because the tracer is streaking to indicate the direction of flow over time. Kind of confusing, but I've got a handout I'm going to give you so that we can practice streak lines. In fact, maybe I didn't get it from the printer yet. All right, let me go get that handout. Just a moment. Well, maybe I didn't even send it to the printer. That'll take a second. Luckily. All right. So we've got 4 different periods of time. I've provided you with a little graph paper so that you can try sketching the path line and the streak line. These arrows are indicating the flow direction. So for the first 3 seconds, the flow's to the right. Then the flow is down. Then it is left and down, and then it is to the right again. it's easy to draw the path line. So you can just draw the path line directly. But you'll notice that here in part 2, where I ask you to draw the streak line, there's sort of like scratch paper on the right. And the reason for that is that you have to kind of get an idea of the shape of it before you place it at the origin. Because you only know where it's going to end. You don't know where the line is going to start. Because remember, in a streak line, the beginning of the streak line is off in space as dictated by the flow movement over time. And here is like the present. It's where your pencil still is. Now here is the hint on how to draw these. You should move the paper in the direction that the flow is indicated for drawing the streak line. So here on the scratch paper, you put your pencil down and then you move the paper in the direction indicated by the arrows instead of moving your hand. And if you do that, then you can get an idea of the shape of the streak line. So you'd move your hand to the right for the first segment of time, and just to simplify things, when the flow is going at an angle, you'll notice in the description that it says that the velocity is 1.41 times faster, and that's simply so that you can just use one block for each of the increments in time. And so it's moving one block to the right during the first time and one block per second down, and then even in period 3 it's moving one block, but it's at an angle, so obviously the velocity would have to be a little bit faster. All right, so we've got some time. You can talk amongst yourselves. I've got the solution. I'll be circulating around to see how you get it. But let's see if we can do path lines and streak lines. Mm-hmm. What? Yep. That's right. The reason why I've given you this extra scratch paper is so you can get the shape of the streak line and then translate that shape onto the other segment. Okay, everyone got the path line pretty easily, right? No trouble with the path line? The streak line's a little trickier, and the best way I've thought of in like 11 years of teaching fluid mechanics to draw that is to move your paper rather than moving your hand. And the reason why is that the paper is the flow field. You think of it as, what if you had a big pool of water that's sloshing around in different directions and you're pouring a tracer into the same spot in that fluid? And so what this is showing, you can see that this is like a little bit more uneven and kind of jagged. It's because I'm just trying to figure out what is the shape of the streak line look like. And so my pencil started here in the lower right-hand corner, and then the flow was to the right, and so I was moving the paper and holding my hand steady, and so 1, 2, 3 seconds, because the flow was moving to the right. So if the flow is moving to the right, then that means that this, at the end of that first time period, is the dye that's just now being injected, and the tracer that was originally injected is here furthest to the right. Then if the flow is moving down, then that's where this line segment came from, and so on. And so then once you have this shape, then you transfer it to B, because this was at the end of the time period. This is at time equals 11. And so where on the streak line is time 0, this is time 0 on the streak line. This was when we barely first started injecting the tracer. So here's time 0, and then B is time 11. Okay, are there questions about that? Yeah, we've got 4 time periods, and I think the easiest way to do it is just to get the shape of it starting at time 0, and then translate the shape onto the correct location in a second step. Okay, so you can already get started on the next homework assignment. We've covered a few things today that I think will enable you to start working on those problems that are due on Tuesday. So I'll see you in class on Thursday, and we'll continue talking about flow movement. Have a good day.